Well, hello everybody. My name's Simon. If you don't know, I am the founder and CEO of DCI Industries. Started DCI Industries about 15 years ago, and in that time have played with every kind of solar system you can think of. And what I want to talk to you today about is the difference between grid connect, hybrid and off-grid, and primarily hybrid and off-grid, because there's a lot of confusion in the industry and online, unfortunately, by a lot of people who are trying to sell you something and they don't know what they're talking about. So let's jump into it. I have my trusty whiteboard markers and I'm going to try and draw some pretty pictures, so see if you can keep up. The main feature of everything we're going to talk about with solar is the property. Whatever it is that we're trying to power up. We'll just call this the house. So whether you have got grid connect, hybrid or solar, what we're trying to do is get some kind of energy into our home. So what we have with normal power system, you have your switchboard on the side of the house. We'll call that your inverter. From here, we are going to have, let's put some solar panels on the roof as well. So, your home uses power out of your switchboard to power everything. Traditionally, you're going to come from the power lines into your switchboard, and that's going to power everything. What we do with solar is we run to our DC side from our solar panels, and then that AC side is going to go into our switchboard. And what happens with a traditional solar system with a grid connect is that our solar system is going to monitor, let's say we're at 230 volts from the grid. What your solar inverter is going to do is go, cool, I can see that 230 volts. I'm going to make myself 235 volts. And so now what happens is when you draw electricity off into the home, electricity follows the path of least resistance. The higher the voltage, the less resistance there is. So it is going to choose to use this power at 235 volts over the 230 that's coming from the grid. So you will effectively use your solar power at the moment that it's produced into your home. Let me grab a red one. So solar is going to come down. It's a terrible arrow. It's going to go into your switchboard to the loads in the house. Then let's say there's only 1 kilowatt there. We're producing 2 kilowatt. One's being consumed. You're producing 2. 1 kilowatt is going to go back out to the grid. Because 235 volts is higher than 230 volts, it's got enough pressure to push against the electrons coming in from the grid, and it's going to push the excess back out to the grid. That is your standard solar system, grid connect. Okay, hybrid. Our hybrid solar system operates on a very similar setup. We've got our solar panel, we're going to have our grid, we're going to have our inverter. Actually, let's just use this so we can see it all. I'll put it over here. I'll put my DC there, my AC there. You've got your switchboard, and effectively, we're doing the exact same setup. We have our connection from the power line into our switchboard. We're going to have our solar go into our inverter, and then our inverter is going to go into our switchboard. Operates exactly the same as what we had going on. But what we're going to now do is add a battery. That battery kind of doesn't fit anywhere yet. You'll notice with any hybrid solar system there is either an energy meter or a CT meter which monitors what way the power is flowing. And it's going to sit back at this point in the switchboard, monitoring that main incoming cable. If it sees power going out this way, there will be a communication cable from that CT back to your inverter. That's going to say, hey, instantaneously at the speed of electricity, there is something trying to go back to the grid. Rather than allowing it to come down here to the grid, how about we take it and we push it into the battery? And so that is going to monitor how much is going to the grid, and it's now going to divert that much power into your battery. Once your battery is full, all the way up to the top, then any excess that you produce will continue to go back like a normal Grid Connect system, and it will push the excess back out to the grid. If you have this same energy meter and it's, let's say, export limited, what that does is see any power going this way. It says, battery's full, I can't put it there. I'm going to ramp down the production capacity of my inverter so that I don't feed anything back to the grid. So it's just matching then whatever's going into the house from the switchboard. It's just going to make sure it only produces that much. Even though your solar may be able to produce a whole lot more because it's the middle of a sunny day, battery's full, you've got a zero export, and your house is only using 1 kilowatt out of your 10 kilowatt solar system, the inverter will ramp itself down to produce only 1 kilowatt because there's nowhere for it to go. Now, where hybrids have some limitations is in their blackout protection and backup functionality. So, most hybrid systems have a couple of conditions, and it's why they're hybrid and not off-grid. A hybrid system requires regular connection to mains power so that it can regulate and balance itself against an external source. It needs to see pretty regularly. Most manufacturers, if you dig into it, are generally saying that it needs to basically be connected to the grid at least once a week. Otherwise, it will end up out of phase, like the frequency will fall out of parameters and the voltage can fall out. It kind of relies on the grid to find a reference point on a regular basis. So they're not designed to run long-term disconnected from the grid on a hybrid inverter. They're not built for it. So that's one thing. So it needs its 240 volt, 50 hertz regulation basically managed by the grid. The other thing it needs is when we go to back out, when we run in hybrid mode, which is now the other direction. So we've filled the battery up during the day, the excess has gone back to the grid. Now it's night time, we have no sun, but we're still drawing power into the house, but our battery's full. So what happens is the inverter goes, well, before I take anything from the grid, priority usage of the battery first. So let's start drawing the battery down, and we're going to start using up the capacity in the battery. That's going to feed back into the house. You're still connected to the grid. Now, here is where hybrid gets really interesting. Let's say you turn a bunch of stuff on and we've got a, let's call this a 5 kilowatt inverter. You draw 7 kilowatts out of here. Actually, for the demonstration, let's not go so extreme. Let's say you draw 5 kilowatts. You plug the kettle, toaster and a couple other things on all at once and boom, big inrush surge, bang, 5 kilowatts. The battery is probably only going to pull 3 kilowatts, even though it's nearly full, and it'll take the other 2 off the top part of that peak off the grid. Now what this does, it reduces the amount of pressure that has to be forced off that battery to provide the power. We'll take most of it from the battery, it'll take the top part, and if we draw this into, let's go over here, into a graph, if your power usage is going along, turn something on, and then we have this big spike here. We turn this full 5 kilowatts on. What happens here with a hybrid system is it will go, let's just cap it there. We'll take this chunk off the battery, and this big spike top section, let's take that off the grid because it's going to get there easier and it's not going to put so much pressure on the battery. Now, obviously it's not having a logical conversation. This is all electronics that does this. But this is where hybrid systems work. So this is also why you've got your 5 kilowatt inverter here. Under normal operations, it can give you 20 amps. It has a backup function for when the grid goes down, and you find that backup function on that second line, backup might only be 10 amps. Why is that? That is to stop you from overloading that battery and the inverter when it needs to create that big spike of power. So because it's not designed to do this, it will limit how much power you can get out of that backup scenario. So you can't back up the full capacity of the inverter on most hybrid systems. There are some out there that you can get full capacity of the inverter on backup, but you've got to obviously get high-end equipment that can do that. Most of your mid-tier and below hybrid inverters can't do that. So that is some of the big limitations with hybrid. They're not designed to be disconnected from the grid for long periods of time, and they generally have a limited backup power supply. Another thing that you'll find with a lot of hybrid systems, once they're in backup mode, yes, you've got limited power, but a lot of them won't actually produce directly off the solar panel and create a full standalone system. They will only give you whatever is left in your battery. So at the time that the grid goes down, your battery is at 25%, and you cut off, let's say you cut off at 15%, you only have 10% of your battery before you're completely out of power, and even your hybrid system is not going to produce because it only is designed to work in this backup mode. So that brings us to my favorite and what we do with off-grid systems. Now we're going to play a very similar scenario. We've got our house, we've got our panels. We're going to have a grid. We're going to have our, for ease of illustration, let's call it our inverter. Now, depends if it's AC coupled, DC coupled, there may be charge controllers. This is just our off-grid inversion system. It has a battery. We have our switchboard. Now, this system is designed to work with a completely different set of batteries. You'll find most hybrid batteries and most off-grid batteries are completely different. You find very few hybrid systems. You'll find hybrid systems that use off-grid compatible batteries, but systems that are primarily hybrid systems only, you'll find you can't augment them to an off-grid system and the batteries aren't compatible because they can't handle this big peak discharge that we're about to talk about. So what happens is your solar is going to go into your inverter. Your inverter is going to then provide the power into the switchboard, and then it's either going to charge or discharge off the battery as required. So what's going to happen is you're going to use your generated power as quick as, as you use it, power your home. Excess, charge battery. When you need more than what you're producing off your solar, you're going to pull that back off your battery. This is a complete power system. Never ever needs reference to the grid. They are designed to be full standalone. This is off-grid. This is why they're different. Now, if we have the grid, the difference here is the grid is going to go directly to our off-grid inverter system. It is only going to come into play. There is effectively a switch inside the actual inverter. It stays electrically disconnected unless it needs it for backup power. So what this means is no matter what happens on the grid side, 99% of your system life, this system never connects to the grid unless you've undersized your system and you're relying on the grid. But if your system is designed right, you operate completely autonomously from the grid. Until you get a week of bad weather, the sun doesn't come out for 3 days, your batteries run too low, we get to 20% in the batteries, the inverter says, oh, we're at 20%, I need some charge from somewhere, can't get it from the solar, let me connect the grid and bring that in as a charge current. Now, the difference with off-grid systems as well, these are not bi-directional. Unless you're running Selectronic in a hybrid mode, whole nother conversation, they can do it. But ultimately, these are just acting as a battery charger. As soon as that battery is back up to, let's say, in our standard systems, 35%, then it says, cool, we're at 35%, I'm safe again, disconnect the grid, get rid of it. And so now you're not electrically connected to the grid. This has several advantages. One, if you get brownouts on your power lines, that's not going to affect your system. It will affect you in a hybrid system. One of the reasons it affects you is because the grid, that main power supply that is not your system, in both off-grid and in hybrid, becomes the controlling voltage and frequency for your system. So if this starts to spike with the voltage, or it starts to drop the frequency or drop the voltage for a brownout, your whole system will match it until it falls out of parameter. It will probably shut down for a second, disconnect and start itself again. So you'll still get some issues with brownouts with a hybrid system. Obviously with a grid connect, as soon as the grid goes out of balance, like if the voltage or the frequency drops out or you lose the grid, you just have no power. Hybrid, you'll have that backup from your battery, from your system. And with an off-grid, they're designed to have never been connected to the grid. What that means is if the grid drops out, it just breaks that. This system remains uninterrupted. You will have no idea that that system even stopped working. Your off-grid system will just have no backup power source at that point. You can create a manual transfer switch or an automatic transfer switch at that secondary point and go from grid to generator as a third tier of backup power supply, but again, that's probably a little too advanced for what we're talking about here. So the advantage of this is no matter what happens on the grid side, your power system is completely untouched. This comes into another thing that I see as a very real threat coming down for people who have grid connect and hybrid systems, especially hybrid systems. And that is the fact that we are moving into this time where we are going to have the ability for the government and the power networks to be able to force discharge your home batteries and your EVs back onto the grid in the case of emergencies. How do we know this? They've already done the tests and trials and it's been a great success. And what they tested and tried was to high frequency signal down the power lines, trigger the inverters, not an off-grid system, in a hybrid, and force it to discharge the home battery back onto the grid without any control from the homeowner. They just high frequency. This is why you'll find all your hybrid inverters are grid interactive. If they are approved for use in Australia, they must be grid interactive. Off-grid doesn't have to be because they are designed to be standalone. They're not designed to be controlled by the grid. So that is a really big consideration going forward. A hybrid system, you may wake up in the middle of a storm going, great, at least I've got my battery, and find out that an hour prior that the network has actually pinged your inverter and everyone on your street sucked all your batteries dry trying to prop up the network, and it still had a failure. But now you have no power left in your batteries and your hybrid system won't produce from your solar panels through the inverter to operate as a full standalone system, and you are now as good as a grid connect system. You have no power left. So that's a very real scenario we're staring down the barrel of. An off-grid system, that can't occur. You are completely autonomous and completely separate. Now, back to the batteries. The reason that we have to have different batteries and high quality batteries in off-grid, and this is the difference. If you don't have high quality batteries, you're going to find they're going to die quickly because of that graph we had before, where your power usage does this during the day. These big spikes are where this battery and that inverter have to go from 0 to flat out and back to 0 or near enough on our graph to provide the power as you need it. So that's like going idle, 100% and back to idle. And we need this battery to do that 6,000 times without having a failure. There aren't many batteries that are going to do that. So what happens with a cheaper battery is that thump, thump, thump of full voltage, nothing, or full current, nothing, full current, can cause cell collapse. If your cells collapse inside your battery is shot, especially with anything that is AGM, gel, or lithium, any types of lithium. They're sealed units. They're not maintainable, which means if you collapse a cell, effectively you create a short circuit and destroy the battery. It's now useless. You've got to get rid of it. If you have gel or AGM, if it's more than 6 months from when the battery bank was put in and you have a collapsed cell, if you had a dead battery, you can't just replace one battery. You actually have to replace the entire battery bank, and that is because you end up with differing internal resistances on your batteries. One will become a load, one will become the driver, and you'll create a circulating current. You'll kill your entire battery bank in probably 3 to 6 months. Even though you thought you were doing the right thing by replacing the dead battery, if your system is, let's say, 6 to 12 months or older, you can't put a new battery into an existing battery bank. Keep that in mind. Lithiums have the capability of being able to just be individual cells, and they're completely individually managed, so you can replace individual cells or add to them. Now, back to our battery discussion. You need quality on those two parts of your system primarily because of this. Because when you boil the kettle, turn the electric cooking on, the hot water kicks in, those power loads, any large power load is going to go from idle to full charge or a good chunk of power very, very fast, like instantaneously fast. And your equipment needs to be able to keep up with that. If you skimp out on these components, you are going to kill your system sooner because they just don't have the integrity inside them to last doing this big heavy charge discharge. Now, the caveat to that is if you've got cheap equipment and it never does hard work. So let's say you've got a 5 kilowatt inverter and you never draw more than 1 kilowatt off it. You've got, let's say, a gel battery bank, and they're relatively cheap batteries, and it's let's say it's 40 kilowatt hours worth of battery storage in your gel batteries, or your AGM batteries, sorry, which are the cheapest of any kind of off-grid solar battery. So let's say you've got some cheap AGMs, you've got 40 kilowatt hours, and you never draw more than, well, what would we say, a kilowatt. So, you know, if you never draw more than a kilowatt, those batteries will actually probably last you okay. But you're buying a 40 kilowatt hour battery bank so that you never draw more than 1 kilowatt off it. Kind of seems like massive overkill just to make sure you don't damage your equipment. If you go start drawing these big spike currents out of them, you'll find that cheap gear just won't last. So, here's something else you need to consider on the battery side of things. Most lithiums, check the manufacturer's data, have a C1 or a C.5 rating. Effectively, C1, for ease of explanation, you have a lithium, and let's call this, these are what we use, the LFPs or the LiFePO4, same chemistry. It's just a different name for the same thing. Let's say this is a 5 kilowatt. So 5 kilowatts is 5,000 watts. 5 kilowatt hours is 5,000 watts running for 1 hour. That's 5 kilowatt hours. You will find your batteries are listed in kilowatt hours. It's the volume of power, which is how much power it can deliver over a period of time. So 5,000 watts over an hour is 5 kilowatt hours. Now, what you've got to look at, your C rating, is your discharge rating. Why it's a C, I don't know. Anyway, well, I do, but anyway, we won't go into that. So if it's a C1, it means it can deliver its entire capacity over the period of 1 hour. So that means a 5 kilowatt hour lithium battery can discharge 5,000 watts at any one time. And it can sustain that for a full hour and deplete the entire battery without doing any damage to the internal cells. Let's go to what we were talking about with the AGM batteries. And you'll find that your gel AGM, your lead acid, they all have a C rating. Generally, you're looking at C20. All right, so on a C20 rating, what that means is you need to take the capacity of your batteries. So let's say we've got a big battery bank. Let's say we've got 40 kilowatts like we were speaking about before. So that's 40,000 watts. The C20 rating means that 40,000 watts has to be divided by 20, which gives us 2,000 watts. So at a C20 rating, this battery bank can only deliver 2 kilowatts of power at any one time, 2,000 watts. So in that scenario, if you have a 3 kilowatt inverter that this battery bank is connected to, that's our maximum. If you draw 3 kilowatts peak out of those batteries, you're starting to do damage because you're exceeding the rated maximum output of that battery bank. Most people don't realize this C rating and realize that it is actually designed by the manufacturer as the discharge and output limit of that battery bank. So to overcome this, you would need to go to, what do we need to go to? 60. You would have to go to 60 kilowatt hours to get that, when it's divided by 20, to 3,000 watts, just so you can run your 3 kilowatt inverter. And if you don't do that, you're damaging your batteries. So this is why lithiums make so much more sense in a modern scenario. They are going to be cheaper than the big battery bank you have to purchase to be able to overcome this. So one 5 kilowatt hour lithium battery can give you 5,000 watts. You've got to build a 60,000 watt or 60 kilowatt hour battery bank to be able to provide a 3 kilowatt inverter if it has a C20 rating. Most of your cheap batteries have a C100 rating. So when you take 60,000 watts divided by 100, you get 600 watts is your maximum output that you can take off that big battery bank. You'll find that on your cheap batteries, so watch out. This is why we use lithiums. So I hope that has not got too technical for you, covered off some stuff. Effectively, the reason that we build modern off-grid systems the way we do, and especially our SIAB systems, where we do use lithium, it is for a number of reasons. One is the footprint. They're a much physically smaller area. Two, they have a higher cycle life, which is one full charge, one full discharge is one cycle. And so most of your AGMs, if you're using them down to only 40%, you're probably at about 2,500 cycles, whereas your lithium batteries can be discharged down to 90%, so 10% off the bottom, and all the way back up is one cycle, and you'll get 6,000 of those. So the amount of power you can run through a lithium battery system is way, way higher than the more traditional systems. The other thing with your good lithium batteries is, as I said, you can add to them, and if you have a faulty one, you can replace it without having any risk of like new and old battery issues. The other thing that you're going to find with the lithiums is that they have that peak output capability that most of the other battery systems don't, and not for the capacity size. So when you go to turn all that power on, dump a huge amount of power in a short period of time and turn it off again, those batteries are going to handle that kind of usage, and you're not going to have the issues of collapsed cells and other problems. So in closing, this is why it is so important to have high quality equipment, because in those scenarios when you're asking it to do a lot of work and do it consistently and not break down on you, you can't ask that of cheap equipment and expect it to work. So that's why we don't do a great deal in the bottom end small systems. It's very difficult to have a full off-grid system in the $5,000 range that is going to give you that kind of performance and make sure that nothing goes wrong. I will catch you later. I hope this has been useful. If you want us to, or you want me to run through any other information about off-grid solar, leave it in the comments. It helps us to know what you guys would like to see, and who knows, maybe we can turn that into the next video we do. All right, take care.